for example, UT has a high salary, so we get high score 8. Maybe Ryerson or TMU has a lower salary, you get a low score of 5. So each criteria has a weight, and each of the alternatives or choices or decisions, we give it a score accordingly, and we calculate the total weighted score, and whichever criteria has the highest total weighted score, we choose that, we make that decision, or we choose that alternative. Right? So it's very simple. You can imagine highly used in everyday work, making decisions, right? Simple to use. Then we get even more sophisticated with the scoring model using this so-called analytic hierarchy process, or AHP. Here we have a graphical representation giving the depiction of the hierarchy of the problem in terms of the goal, the criteria to be used, and the decision alternatives. So here, as an example, maybe your log loss, and you sell 2 brushes in your stores, and you want to decide which manufacturer to buy your toothbrush from. Okay, so the goal is to select the best toothbrush manufacturer. What are our criteria? So a criteria is cost, right? We want to minimize our costs of buying the toothbrush to sell in a store. How reliable is the manufacturer in terms of being able to promise their delivery dates and not be late, and be able to deliver the numbers, the quantity we order, and not be unable to fulfill our quantity. And we also want to look at the delivery time. When we place an order, how fast can they get it to us, right? So obviously the lower cost would be better, the more reliable is better, and the shorter delivery time is better. And then we have 3 potential companies that we can buy from: Cornell, Brush Pick, and Pickleball. Right? So with this AHP method, it requires the decision maker to provide judgments about the relative importance of each criteria. So, you'd be asked how much more important is cost compared to reliability, how much is cost compared to delivery time. Right? And it involves us making a series of pairwise comparison between the alternatives for each criteria. And then the decision maker will be asked, okay, let's look at cost. How much better is Cornell compared to Brush Pick? How much is better Cornell compared to Pickleball? And we do the same thing for reliability and delivery time. The output of the AHP process is a priority ranking or weighted score for the decision alternatives. So basically, AHP is just a sophisticated scoring model. Okay, so instead of this simple, having weights from 1 to 5, we have a more complicated way to calculate the weights. And instead of having just the scores from 1 to 10, we have a more complex way to calculate the score. Okay, but at the end of the day, the goal is to calculate this total weighted score, and whichever alternatives has the highest weight total score, we choose that alternative. Okay. Okay, so these are the steps, but maybe it is. So basically, you have to list your overall goal, criteria, and alternatives. And then the next thing you need to do is you need to come up with the weights for each criteria. Okay, so the next step is come up with the weights for each criteria, and also to perform a so-called consistency check. Then the next step is come up with the score ratings for each of the alternatives. Okay, so that's the third step. Final step is to put the summary table together and calculate the total weighted score. So that's basically the 4 steps that's involved. Okay, first you calculate the weights for the criteria and perform a consistency check. Next you calculate the ratings for each alternatives and perform a consistency check. And then finally you put the matrix together and calculate the total weighted score. Okay, so let's look at the example over here. So we'll look at this example of choosing a job. So after finishing her PhD, Jane got 3 job offers and become a professor at 3 different universities. I guess I should update my name over here. So U of T, UBC in Vancouver, Ryerson, or TMU downtown. Now she needs to decide which job to choose. She has 4 objective or criteria. a high starting salary, quality of life in the city where the job is located, reputation of the university, and whether the job location is near family and relatives. So James feels that salary is strongly preferred than quality and gives a comparison value of 5. And so how do we get this 5? So salary is strongly preferred than quality. So the comparison values come from this table over here. So if something is strongly preferred, then you can give it a comparison value of either 5 or 4. Right? And then Jane also says that salary is moderately preferred than reputation, and gives it a comparison value of 2. So something that's so-called moderately preferred, and then you can look up the table here, can be given a value either 3 or 2, and we assign a value of 2 there. Okay. So based on how Jane feels comparing one criteria to another criteria, we would assign an appropriate comparison value. Okay, so let's start to solve her problem here. Uh-oh. I forgot to print this set. I will be right back.
His handwriting. Yeah, sometimes I'll be sitting there like kind of numbers that you get used to it after a while, and you get desensitized. You also just get like used to how it progresses as time passes.
Spring is coming. I'm so excited.
I should be technically it should be spring.
Because of David saying you're saying spring came.
No, because also isn't March technically spring?
No.
The official date is March 20th.
Oh.
Better.
See, I was right, March. See, I was right.
But it also depends on Groundhog Day. Because then
not the season lore. I'm sitting there like, how does she know all this? I'm like, I could care less about Groundhog Day. I just look at the sky, I'm like, ah shit, it's spring again. Yeah, the tree, well, it's hard to see because the tree's kind of naked right now, like, no leaves.
it's just a skeleton.
Skeletal trees.
6, 7, 8, 9, 10 degrees.
I actually could have probably afforded to wear something like
And this is what finally wake up earlier.
Groundhog Day is in February. I thought it was in March.
us.
Oh.
Oh.
You
When's the-
misled us with your.
No.
Would you?
Wait. When is the first day of spring?
Why does this sound disgusting to me? Lavender much.
See, spring is March 20th to June 20th.
Okay, I thought when spring starts.
Yeah.
June 20th. That's like the weird.
That's like summer.
I thought summer starts in June. Oh wait, no, summer starts June 21st. Summer solstice.
No, but the thing is that May is so
May?
May here and so
I know, and that's why I hate it, especially because I was born during this month.
May?
Yeah, May 15. We talked about this
Yeah.
last week.
Okay, so list the overall goal criteria between alternatives. So in this case, our so-called goal is select the best job. And then our criterias, we have 3 or 4. We have salary, we have quality of life, we have the reputation of the school, and then we have the location, whether it's near relatives or not. And then in terms of the decisions or alternatives, we have 3. We have U of T, we have UBC, and I guess I should call it, you know what, I'll keep it Ryerson for one last time, so that I don't confuse you, and I'll change it for next time. Same thing for quality, we have to compare the schools. Okay, so the goal is to select the best job. The criteria is salary, quality, your reputation, and location. And then for each of the criteria, we have to compare the school. So we would compare the schools in terms of salary, we compare the schools in terms of quality, we compare the schools in terms of reputation, and we compare the schools in terms of location. Okay, then we have to basically come up with the weights for each criteria. So we have this, we start with this comparison matrix. And so for the comparison matrix, we have salary, quality of life, reputation, location, and same thing down here. And so we would start putting down the numbers. So salary compared to quality is 5. So therefore, salary compared to quality is 5. And so, quality compared to salary would be the opposite. So this is simply 1/5. And then salary compared to reputation is 2. So salary compared to reputation is 2. And so once again, the opposite here, reputation compared to salary would be 1/2. Okay. So that's basically, given the preference values here, then you would just give it a reciprocal rating to compare the other one, right? Okay, so moving along, we have salary to location is 4. And so location to salary would be 1/4. Okay? So we basically do this. So I will simply fill in the rest. It says reputation to quality is 2. And so quality to reputation will be 1/2. Okay, so I will complete filling in the rest of the values that are given. Then we total everything together here. Okay, so next we total everything over here. Then we have to normalize the matrix. And to normalize the matrix, basically we take each cell and divided by their respective total, right? So this basically, if you take 1 divided by 39 over 20, then you get that. And you take 1/5 divided by 39 over 20, then you get that, okay? So basically to do this, you have to take take the value for each column. And divide by the total. So that's how we so-called normalize the matrix. Once we do that, then we will calculate the average weights here. So we'll calculate the average weights here. And this becomes a so-called priority vector, which is then the weights for each of our criteria. So this column here then gives us the weights or importance of each of our criteria. Okay, so that's how we calculate the weights instead of just a number from 1 to 5. Then we have to check whether Jane's preferences that she gives us is consistent or not. That's the next step. And so what is this consistency check about? Okay, so this process requires the person to tell us, how one criteria or how one criteria compares to another, right? So for example, if criterion A compared to B has a numerical rating of 3, and if B compared to C has a numerical rating of 2, then perfect consistency when you compare A directly to C would have a numerical rating of 6. If A compared to C assigned by the decision maker was either 4 or 5, then some inconsistency would exist among the comparisons. So AHP measures consistency of the comparisons by computing something called the consistency ratio. A ratio greater than 0.1 indicates some inconsistency is present, and maybe the person should be asked to reevaluate their comparisons. So how do we calculate this consistency ratio? Well, there's 3 steps. So there's the steps over here to calculate the consistency ratio. Okay, so let's do that. Okay, so the maybe I can just stick with the rest here. So to calculate the consistency ratio, the first step is you take your comparison matrix and you multiply by the so-called priority vector, right? So we take this matrix that we have here and we multiply by this column here, right? And maybe I will go back here just to make sure you remember. Okay, and so we get this value. Let me just make sure you remember your matrix algebra here. So basically to get this value, we take this row and times this column. To get this number here, we take the second row and times the column, right? So basically to get that number here is basically we take row 1 and multiply by the column. And so this would be 115, 50986, and 2433, and then 41466. And then of course the second value, you will take the row 2 and times the column, right? Next, we have to calculate this so-called lambda max value, and basically, we have to take the resulting value here and divide it by the corresponding priority value there, okay? And we take the next resulting value and divide it by the corresponding value, okay? And then we divide it by 1/4, and the reason why it's 4 is because so you have to divide by 1/n, where n is the size of the matrix. So we divide 1/4 because we have a 4x4 matrix. Next, we calculate the consistency index by taking our lambda max value minus n. And again, n is 4 because we have a 4x4 matrix as well here. And divide by n minus 1 here. So for us, n basically is equal to 4. Right? Finally, to calculate the consistency ratio, we take the consistency index and divide by the random index. So our consistency index is 0.017, and the random index is 0.9. Well, how do we get 0.9? So here in this table, this is a so-called random index, is a consistency index of a randomly generated pairwise comparison. So for us, we have a size of matrix. For us, n is 4, and so the random index is 0.9. So the random index is basically just randomly making comparisons and seeing what the index value you get. Okay. So this is from table on page 5 for n equals 4x4 matrix. And so our consistency ratio is less than 0.1, so therefore James comparisons are consistent. Then, now, we're going to compare the jobs with each other with respect to salary and come up with a rating value. We'll compare the jobs with respect to quality and come up with a rating values for each job. So over here, we start with quality here. So we're comparing the jobs with respect to quality. So the 3 jobs are U of T, UBC, and Ryerson. And first, we start with the comparison matrix. And that is basically given in the problem here already, right? So it didn't require us to construct our own. It did not because it's already given. So there's the comparison matrix. The 3 jobs with respect to quality, right? Again, we total the columns. Okay, we total the columns. And again, we normalize it by taking each of the value and dividing by the total. Right? And then we take the average. So that becomes our ratings for U of T in terms of quality, for UBC in terms of quality, and for Ryerson in terms of quality. We also have to perform a consistency check to make sure the comparison between the schools is consistent. So once again, we take the comparison matrix, we multiply by the corresponding vector value, and we get the following results. And then we calculate lambda max by taking the corresponding result and dividing by the corresponding value here. And for us, n is equal to 3x3 matrix. You can see we have a 3x3 matrix over here, so n is equal to 3. And again, consistency ratio is lambda max minus n over n minus 1, so we get the n is 3 here. And again, consistency ratio is CI was RI. For this value here, again, from page 5 for n equals 3. So again, when you look at the random index value for n equals 3, that's how you get the 0.558 there, right? And again, the value is less than 0.1, and so her comparisons with the between the university in terms of quality is consistent. So we have to basically do the same thing for salary, do the same thing for reputation, do the same thing for location. So we then compare the jobs with respect to salary here. So we start with our matrix, we total it, we normalize it, and then we take the average. In this salary comparison, we note that the columns in the normalized matrix is identical, right? We note that the columns in the normalized matrix is identical. So this illustrates that we have perfect consistency, and so there's no need to perform a consistency check here, right? Then we compare the jobs with respect to reputation. Again, we start with the comparison matrix, total it up, divide by the total, take the average. I didn't show the calculations here, but if you perform the consistency check, you'll see that the comparisons are consistent. Finally, we compare the jobs with the location. Again, if you make the calculation for the consistency check, you'll also see that it is consistent. Okay? So we create this matrix for for the comparison, and then we have to create a matrix for each of the criteria. So now we kind of put everything together in a summary table. Okay, put everything together in a summary table. So there's my criteria. The weights are coming from this table here. Okay, the weights are coming from this table here. So we see we have 0.551 for salary, 0.0986 for quality, and so forth. Okay, so 5115, and then 0986, 2433, and 1466. So this is basically from the weights table on page 5. Then we copy the ratings from the tables here. So if you look at the ratings for reputation, then you would be, when you look at the ratings for, say, location, so you'd be looking at the location table, and then there's the ratings, and so that's what we would put here. So in terms of location, the rating for U of T is 0685. The rating for UBC is 4257. And the rating for Ryerson is 5056. Okay, so basically we use those averages to populate the summary ratings table here. And of course, if we want to populate the reputation, then we would be looking at the reputation table here. And then we would be picking those values, and we would be filling in there. So OAA2, 6687, and 2431. Okay, so we fill in the ratings from the previous calculations. And then we calculate the total weighted score. Okay, so basically pick the weights times that, take the weight times that, and so on, and come up with the corresponding total weighted score. And it seems like that the highest weighted score is UBC. And so therefore choose UBC. Again, it's a weighted factor model. You have a more complicated way to calculate the weights for the criteria. You have a more complicated way to calculate the ratings for the jobs. But ultimately, it's just a weighted factor scoring model. I don't know, you can try it out for next time when you have a decision to make. See how that plays out for you, right? Okay, so that's the first part, and that wraps up the chapter 14 for us. Okay, so now we're going to go into the chapter 13 here. And look at various decision-making strategies as well as the use of decision trees. So we'll bring it to two parts. Today we'll look at decision-making strategies, and then next class we'll look at decision trees. Okay, so we'll look at some common decision-making strategies. The first one is called a max-min strategy. So this is good for the pessimist or conservative decision maker. And therefore, so for each alternative or decision, you pick the worst thing that can happen to you, and then you choose a decision that is basically best of the worst. So here we have two decisions and two states. So maybe this is recession, maybe this is no recession. And then there would be the payoff, okay? So we call this the payoff matrix. And so for each decision, we see what's the worst that can happen to us. If you choose decision D1, the worst thing that happens to you is you end up with $400. If you choose a decision D2, the worst thing that can happen to you is you get $450. So between 400 and 450, this is so-called best of the worst. Okay, so that's basically best of the worst. And so therefore, we choose D2. However, this strategy may not make sense in some cases. So here we have another set of data. If you choose D1, the worst thing that can happen to you is you end up with 31. If you choose D2, the worst thing that can happen to you is you get 32. And so you would choose D2. However, that just totally don't make sense, right? You have an opportunity to earn $1,000 there, right? and you're giving it up, you know, for literally $1 difference, right? You're giving it up for $1 difference. So, but this opportunity to make 1,000, right? Another strategy is the other extreme. The maxi-max is good for the optimist person. And because you're optimist, therefore for each alternative decision, you pick the best thing that can happen to you, and then you choose the decision that is best of the best. So here again, in this example, the best thing that can happen if we choose D1 is we get 600. Here, the best thing that can happen to us is we get 500 only. And so therefore between 600, we would choose that, right? So this is so-called best of the best. So we choose D1. Okay, so that's the idea here. Again, sometimes it just don't make sense to do it like that. For example, over here, if you choose D1, the best you can end up with is 1002. If you choose D2, the best that you can end up with is 1001. And so, you know, you would choose D1, right? However, this is totally not making sense, because if you choose D1, you run the risk of just ending up with $1, right? And all for like just $1 gain here, right? You run the risk of ending up with just $1 here. So I may end up with $1, right? Okay, next. Next we have so-called Laplace principle, even though they, so here we assume that each state is equally likely to happen, and so we would choose the decision that has the best expected value. Finally, we have a minimax regret here. This is good for the so-called insecure decision maker, and so you would basically try to minimize your maximum regret. So what do we mean by minimize your maximum regret? What does it mean to regret? Suppose you're trying to buy a new laptop, and then you're going into Best Buy pretty much every day and checking out prices. Finally, the price, they had a sale, and you bought it. Okay, 25% off, you bought it. And then the next couple of days, you keep going back to Best Buy and looking at the price. And if the laptop is sold out, well, you're very happy, right? You bought it. But if the price drops down some more, then you feel really sad. You can't eat, you can't sleep. So therefore, maybe you want to minimize your regrets, okay? So this requires you to construct a so-called regret matrix that measures how bad do you feel after if you choose decision DI and then state SJ turns up. So let's look at this problem here with 4 decisions and 4 possible states that can happen. And it says which decision would you make, right? So if you were using the maxi-min approach, then you're the pessimist person. So you would look at the worst thing that can happen to you. So you choose D1, the worst thing can happen, you end up with $0. Here the worst thing is 2, here the worst thing is 0, here the worst thing is 8, is 0. And so if you were using the maxi-min strategy, so-called best of the worst, is this one here. So for best of the worst, you would be basically choosing D2. Which of these decisions would you say this person is a conservative person? Which decision would a person choose for you to say, well, I think that person is a conservative person? Well, I would say D2, right? Because it really doesn't matter what happens, you get your $2. Which of these decisions would you say, wow, you're a gambler? Yeah, I mean, basically it's all none, right? Between D1 and D4, which one is more conservative? Yeah, I would say D1 is more conservative, right? So there's varying degrees. This is ultra conservative. This is a little bit more conservative. This is more risky. This is gambling, right? What if you're maxi-max? Then, well, you're basically an optimist and you're doing best of the best, right? So if you went D1, best is 4, best 2, best 8, best 6. So for best of the best, choose D3. And this is for maxi min. Let me ask you a question. Do you think people become more riskier or more conservative if the amounts were bigger, right? So suppose if it's not $4, it is like, $4,000. Do you think people will start becoming more conservative or become more riskier if the amount of money increases? What do you think?
I think riskier.
Riskier? If the money was bigger?
Like if you look at gambling, the odds of them winning is really low, but they still can buy a large number.
Yeah, but the amount of money you spend is really little.
Oh.
What if what if this is not $8? I say instead of that it's 8,000. So this is the money you get, right? If you choose D1, you'll get $2,000 no matter what. If you choose D1, well, you could get no money, you could get 2,000, you get 4,000, right? So if the money increases instead of $4, 4,000, what do you think? People will go towards becoming more conservative decision or more riskier decision? Any opinion? Would you become more riskier decision or would you choose the more conservative decision if the money amount increased?
More conservative.
Yeah, you want your $2,000 for sure, right? How about the amount of wealth you have? Instead of the money, whatever money amount you have in as your asset, wealth. Let's say you currently have $100,000 in the bank, okay? And then you would choose whatever decision, right? Suppose instead of having 100,000, you now have $1 million in your bank account, okay? So you're much more richer. Would you think you would then start choosing the more conservative alternative, or do you think you'd start choosing the riskier alternative?
I think if you're richer, you're gonna be riskier.
Yeah, I would agree, right? He's like, whatever, $8,000, sure, right? So, again, the decision is kind of based on your asset, based on the amount at play as well, right? And then if we use the Laplace, okay, so we would need to calculate the expected value. And the expected value here is 2.5, 2, 2, and 2. And so how do we get an expected value of 2.5? Well, we have 4 decisions. So equally likely means each has a 25% chance of happening. So we would take 0.25 times the 4, 0.25 times the 4, 0.25 times the 0, 0.25 times the 2, and that basically gives me 2.5. Or, since the probabilities of each state is equal, is really taking the average. Okay, since the probabilities are equal, then it becomes just taking a simple average. Crap, I forgot to put out the sign-in sheet. Anyways, if you need to sign in, please sign in over here. If you need the last class lecture note, let me take it out over here. So you can